Hey guys, welcome back to our third lesson related to rational functions. And today we're going to focus on finding vertical and horizontal asymptotes, mostly analytically. We're going to be given an equation of the rational function, and by manipulating that equation, we're going to try to identify the equations or the locations of all vertical and horizontal asymptotes. And I can't lie, this is one of my actual favorite lessons. And I certainly enjoy finding vertical asymptotes, but I really like the methods that we're going to use for horizontal asymptotes. And I think you'll be particularly enthralled with them as well, I hope. So anyway, what are we going to see in this video today? So we're going to be given a function like f of x equals x divided by the quantity x squared minus 16. And we're going to try to find the equation of all the vertical and horizontal asymptotes, if there are any. Again, there's no guarantee that a rational function has to have, a vertical or horizontal asymptote. So we're going to focus first on verticals. How do you find a vertical asymptote? So again, we're working with our broad definition of a rational function here, f of x equals p of x divided by q of x, where they're both individually polynomials. Assuming that p of x and q of x have no common factors. Okay, that's a bigger deal than sometimes we give it credit for. And a is a zero of q of x, the denominator, then x equals a is going to be a vertical asymptote. Now, believe it or not, that probably sounds like Chinese, and that's okay. In our last video, we were working on finding the domain, right? This is going to piggyback perfectly off of that idea. AKA, we're going to find the zeros of the denominator. If we can find the zeros of the denominator, that's it. That's where our vertical asymptotes are going to sit. So basically, if you think about our last lesson, every number that we excluded from the domain was because that's where the vertical asymptote lived. Okay, so there's a real strong connection between the domain of a rational function and the location of its vertical asymptotes. They seem to be one and the same. Okay, so let's see if we can find these bears. So right off the bat, we're thinking, okay, everything's factored here, which is nice, and nothing cancels. Okay, in other words, the numerator and the denominator did not have any common factors. In other words, nothing canceled. So we're just going to focus on finding the zeros. I would say the zero is at x equals 7, and that is your vertical asymptote. Okay, I'm going to make sure I get everything factored here. So it's x plus 2 all over x plus 7, x minus 7. And now, again, nothing canceled, so that because I had no common factors. And I've got two vertical asymptotes, one at x equals negative 7 and one at x equals positive 7. Now watch what happens here in this next example. We got a real zinger here. I've got my x plus 7 all over my x plus 7, x minus 7. We do have a common factor, okay? We're going to cancel these terms, and I'm left with 1 over x minus 7. So I really only have one vertical asymptote, and that's at x equals positive 7. That is, if I had a nickel for every time a student told me that this function had two vertical asymptotes, one at positive 7 and negative 7, I'd be a very rich person right now. So we've got to get disciplined, and we've got to see the common factor and canceling it. In fact, so you're thinking, well, something's got to be happening at negative 7, right? So when you cancel these terms right here, you still have what was called a discontinuity, but now it's called a hole instead of a vertical asymptote. So we'd say there's a hole at x equals negative 7, and we'll talk a little bit more about holes as we go on. All right, in our fourth example, I don't think I can factor anything, okay? And since that x squared plus 49 can't be factored, we'd say this denominator never does equal 0, and there's no discontinuities. So we have none, no vertical asymptotes, and that's cool. It's always nice to have a continuous function. Okay, now this is going to look like the craziest thing you've ever seen, and that's okay. Let's see if I can zoom in just a tad and get this a little bit bigger. All right, hopefully that helps. All right, so locating or finding horizontal asymptotes. Let f be the rational function given by this really, really scary looking bear. Okay, does this look scary or what? Well, all you really got to focus on is the first term in the numerator, the first term in that denominator. Now, when I look at, when I look at this first term right here, The a sub n is the coefficient, and then I've got my variable x raised to the nth power. Now that nth power is going to tell me the degree of the numerator, okay? So we're saying the degree of the numerator is n. Then, if I look at their first term, I'll say b sub n is the coefficient times I've got my variable raised to the m power. That m is the degree of the denominator. Can't really see it here. I got to scroll down. Okay, so the degree of the denominator is m. So you want to identify, not necessarily always the first term, but the term with the biggest exponent in the numerator, and then identify the term with the biggest exponent in the denominator. Okay, they won't always have these polynomials in standard form. They're going to try to trick you and lure you into some bear traps, and we'll be ready for that. Now, you want to compare the degree of the numerator to the degree of the denominator. And when we compare their degrees, I call this a power fight. Okay? Because a lot of times we use the word power for exponent. So we're going to say this is what we call a power fight. I'm going to compare the degree of the numerator to the degree of the denominator. And the first situation we have is what I like to call small over large. In other words, n is smaller than m. The degree of my numerator is smaller than the degree of my denominator. And if that's the case, you have one horizontal asymptote, and it is the x-axis, or what we like to call y equals 0. So we love to see small over large just because it's instant. It's just y equals 0, we're done. Now, probably the more common one, maybe not, but it's still pretty common, is what I call same over same. Same over same is what I call when the degree of the numerator is the same as the degree of the denominator. And in that case, the line y equals a sub n divided by b sub n is the horizontal asymptote. Now, what do I mean a sub n and b sub n? Remember, a sub n is the coefficient of the biggest term in the numerator, and b sub n is the coefficient of the biggest term in the denominator. So all you're doing is taking the ratio of their coefficients. Okay, and last but not least, we have what's called large over small. Large over small means the degree of the numerator is bigger than the degree of the denominator. In this case, the graph has no horizontal asymptotes, and it's probably going to have what we call an oblique asymptote. So you might have, I'm going to draw a real fun picture for you here. You might have, let's say you do have a vertical right on the y-axis there. You probably can't see it. Let's say we have an oblique is like a slant asymptote. And so you might have a graph that behaves like this, and it kind of sits right in those crevices, so to speak, which is kind of fun. I'll tell you what, we're going to see some wild functions before it's all said and done. I'll tell you that. Okay, so let's work on practicing our horizontal asymptotes. And the moment we say horizontal asymptote, I want you to think power fight. Power fight. Compare the degree of the numerator to the degree of the denominator. So what we've got here, my numerator has a degree of 1. That's the exponent. My denominator has a degree of 2. This is what we call small over large. And that automatically means that there's an asymptote at y equals 0. In our next example, let's see here. Oh, goodness gracious. I forgot to edit those. Okay, so we're going to fudge these as we go. The numerator should be 3x squared, okay? So let's write that down. So the original problem is 3x squared divided by 4x squared minus 1. So now what we have, this is what we call same over same. The degree of my numerator is a 2. The degree of my denominator is a 2. Totally ignoring the minus 1. It has no relevance here. So since we got a degree 2 over degree 2, we call this same over same. And in this case, whenever you have same over same, you take the ratio of the coefficients. So you're going to say y equals 3/4 because I had a coefficient of 3 and a coefficient of 4, so 3/4. Our last example is supposed to be 3x cubed over 4x squared minus 1. And what we've got now is large over small. We have a third degree numerator. We've got a second degree denominator, so degree 3 here, degree 2 there. This is large over small. So we have none. there is no horizontal asymptote. There is going to be an oblique asymptote, and that'll be a conversation for another day. We'll talk about that down the road. Okay, what other fun stuff we got? Okay, so let's see if we can mesh it all together here. We've been given this function. Can you find the vertical and horizontal asymptotes? And I like to try to do both at the same time because it forces us to really focus on the different processes here. How are they different? So for my vertical asymptote, I just want to make sure that I've got everything factored, okay? So the numerator can't be factored. It's already a monomial. The denominator can be factored. And the reason I'm factoring it, if you recall from earlier in the video, we're just confirming that there's no common factors. There's no holes. Nothing canceled. So when is the denominator 0? We're trying to find the zeros of the denominator. We'd say at x equals -4 and x equals +4. So this function has 2 vertical asymptotes. Now switching gears. When we switch from vertical to horizontal, our brains really have to switch gears. I'm not looking for the zeros of the denominator anymore. I'm focusing on what we call a power fight. The degree of the numerator is 1 because of the exponent. The degree of the denominator is 2. This is small over large. And so there's an asymptote at y equals 0. Beautiful. See, how much fun are these? This doesn't require too much work. Does require some thinking, but not too much work. All right. Vertical. Can I find the zeros of the denominator? Well, my numerator is already factored as much as possible. My denominator, I'm going to take out a GCF of x, and then it's going to give me x plus 5, x minus 5, because I had a difference of 2 squares. So I did a lot there. Now you notice we do have a common factor. So I could make a comment that there's a hole at x equals -5, and then I've got a vertical asymptote at x equals 0 because of this term, and x equals +5 because of this term here. So 1 hole, 2 vertical asymptotes for a grand total of 3 discontinuities, we'll say. Now, switching gears, we're looking for the power fight. Degree of the numerator is 1. Degree of the denominator is 3. Hey, that's small over large. Small over large is always y equals 0. I told you horizontal asymptotes are fun. Just a little power fight, not much work to do. Okay. Let's see here. Factor the numerator. Well, that's already done. Factor the denominator? Can't be done. So we'll just say x squared plus 16. So what are the zeros of the denominator? Well, there are none because this expression here is always positive. It will never equal 0. Our conclusion is that there are none. There are no vertical asymptotes. Okay, power fight. We've got a degree of 2 here, degree of 2 there, same over same. Now, when you have same over same, you want the ratio of their coefficients. So I'm going to say I got a coefficient of 2, a coefficient of 1. So 2 divided by 1 is 2. All right. Hey, let's finish with one more here. This green bandit. No substitute for good reps. You know what I'm saying? So we're looking for the zeros of the denominator. Factoring the numerator, I don't think I can factor that. There's really nothing that jumps out at me, so I'm just going to write 5x cubed plus 4. The denominator could be factored into x minus 4, quantity x plus 2. So there's no common factors. That means there's no holes. I've got a vertical asymptote at +4 and another one at x equals -2. Power fight. All right, I got a degree 3 numerator. I got a degree 2 denominator. This is large over small, which means with respect to horizontal asymptotes, there are none. There will be a slant or an oblique asymptote, but yeah, we'll talk about that later. You know what I'm saying? All right, so I hope you feel pretty good about these asymptotes. Really trust the process, focus on the process here, and it'll never steer you wrong. Have a good one.